This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Ever stared at a scientific visualization and wondered if you're actually seeing what the data is trying to tell you?
Happens all the time. It's easy to get lost in the visuals, yeah.
Exactly. This paper tackles that head-on, focusing on how we use color to represent data, especially in geoscience.
Color is powerful, but it can be misleading if not used carefully.
Right. So we're talking about making sure our visualizations are well posed, as the title says. The paper lays out this model of visualization, kind of a three-legged stool: data, visualization, and the user. They're all interconnected, right?
Absolutely. The data gets transformed, the user interprets it, and it's a constant feedback loop. The way you design the visualization directly impacts what the user sees and understands.
I see. And color maps are a huge part of that. We've all seen those rainbow color maps, right?
The infamous JET color map, it looks pretty, but it's scientifically problematic. It distorts the data, you know?
So what's the better approach?
The paper champions using perceptually uniform color spaces like CIELAB instead of RGB. CIELAB better reflects how our eyes actually perceive color.
So our eyes aren't perfect color sensors.
Not at all. Our perception is non-uniform. RGB is simple for computers, but it doesn't match our visual system. CIELAB is a much better fit.
Yeah. And the CIE system is the gold standard for color, right?
Exactly. It's the international standard for color specification. It's all about accurate representation.
CIELAV is a uniform color space. What does that even mean?
It means equal distances in the color space correspond to equal perceived color differences. It's much more intuitive for interpreting data.
So no more visual tricks playing on our eyes?
Precisely. It's about accuracy and avoiding misinterpretations.
And then there's AT, the color difference metric. That's key, isn't it?
Crucial. AD tells you how much two colors differ perceptually. It helps you design color maps with clear distinctions between data points.
So you can actually quantify the difference between colors?
Yes, and that's vital for reproducibility. Someone else can recreate your visualization and get the same results.
Right. The paper also talks about 3D representations of color. Why is that important?
Because it gives you a much better understanding of the relationships between colors. You can see the paths through the color space, which is crucial for designing effective color maps.
So it's not just about picking colors, it's about understanding how they relate to each other.
Exactly. It's about the journey, not just the destination. Makes sense.
The paper introduces Gradient Designer, a software application. What does it do?
It lets you interactively design and explore color maps in different color spaces, seeing the effects in real time. It's all about iterative design.
So you can tweak things and see the immediate impact on your visualization?
Precisely. It's a powerful tool for creating well-posed visualizations.
The software sounds pretty sophisticated. What's it built on?
It's built on Mac OS's Quartz Composer, using a mix of predefined nodes and custom routines. It's designed for speed and interactivity.
And it can even share its output with other applications.
Yes, using Siphon, allowing for integration with VR and other immersive systems. Cool.
The paper uses a seismic tomography model as a case study. Why that dataset?
It's a complex, spatially varying dataset, perfect for testing the effectiveness of different color mapping techniques. It's a real-world challenge.
And what did they find?
They showed how easily RGB can introduce non-linearities, leading to misinterpretations. CIELAB, on the other hand, produced much more accurate and reliable results. Interesting.
The figures in the paper are really striking. They show the difference between RGB and CIELAB so clearly.
The visualizations speak for themselves. The CIELAB maps are much more perceptually uniform, revealing the true features of the data without distortion.
And they even incorporated uncertainty into their visualizations.
Yes, using Aula-E to represent the uncertainty range. It's a clever way to show both the data and its limitations.
So what's the big takeaway from all this?
Careful color map design is crucial for accurate scientific visualization. CIELAB offers a superior approach, providing both accuracy and reproducibility.
It's not just about making pretty pictures. It's about communicating information clearly and accurately. Absolutely. And that's a wrap on this fascinating discussion about well-posed visualizations. Thanks for sharing your expertise.